All right, folks, here we are, and this is the first video for Chapter 5, Section 5-1. So here we are. This is an outline of the entire chapter. 5.1 is the probability distributions. 5.2 is the mean, variance, standard deviation, and expectation. That's the ones I was talking about before, that those terms sound very similar to what we've done before, but they're different. 5.3 is a binomial distribution. It's a very common distribution. And 5.4 is other types of distributions. Now remember, we're in here, Chapter 5, discrete probability distributions. All right, so without further ado, here we are in Section 5.1. Okay, so what is it? What the heck is a probability distribution? Well, the very first thing we need to do, and I'm hoping you're reading, not just listening to me, I hope you're reading this ahead of time. We got to decide, what do we mean by a random variable? So a variable is something that is used to, let's see if we have a good definition here. It's a characteristic or an attribute that can assume different values. So what is your height? What is your weight? What is your IQ? Are you Republican or are you Democrat? Are you sick or are you not sick? Those are things that can assume different values, right? And sometimes they're numbers and sometimes they're categories. A category might be sick or not sick, Republican or Democrat, male or female. A number, of course, would be your height, your weight, and so forth. So here's the example of what he's talking about. I'll let you read that. The key thing here is a random variable is a variable whose values are determined by chance. Now this gets confusing, in my opinion, because sometimes we'll talk about random variables, but you've already done your measurement, okay? You've already tossed the dice. So that head is, in some sense, is not really a random variable. It's not determined by chance anymore. That, in my view, is a data point. So oftentimes the authors, even this author as well as others, are very sloppy with their language here. The random variable, to be precise, is a variable whose values are determined by chance. Once the value is determined by tossing the dice, by flipping the coin, it's not a random variable anymore as much as it is a data point, okay? Now we're going to classify random variables as being discrete or as being continuous. Discrete means that it has a finite number of possible values. I don't like that definition at all. Okay, I'm sorry, I spoke too soon. Discrete variables have a finite number of possible values. That part I agree with. Or an infinite number of values that can be counted. When you say something is counted, another term you might see on the internet, we say that they are denumerable. If it's denumerable, that means it can be counted. So that would be like the number of joggers in the park every day. So there's 20, there's 30, there's 186, whatever it happens to be, okay? They can be counted. How many basketball points do you get? That can be counted, okay? On the other hand, something that can't really be counted, but it has to be measured, we call that a continuous variable. So the temperature goes from 62 degrees to 78 degrees in a 24-hour period. It's passed through every possible number from 62 to 78. There's an infinite number of values, okay? So if you can count it in the sense of how many basketball points do you have or how many children do you have in the classroom, we usually refer to that as a discrete variable. If you're talking about the temperature of the room, things of that sort, IQ, that's a continuous variable. And what will happen later on, we'll see, is that we're going to do some estimating. We're going to estimate a discrete variable using a continuous variable because sometimes it's a lot easier to calculate it that way. But we'll see how that works here in just a bit. So read his example here. I think it's pretty clear. So how do you do this? How do you get this probability distribution? Let's get the definition first. A discrete probability distribution consists of the values a random variable can assume and the corresponding probabilities of the value. So take that sentence apart. The corresponding probabilities, corresponding refers to the particular value, okay? So the typical example we use is flipping a coin. It makes it nice and easy for everybody to remember. So we're flipping the 3 coins. What are the possibilities? You can get 10, 10, 10, tails, 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 tail, tail, head, blah, blah, blah. Okay, so here are the different ways that you can get 0 heads, 1 head, 2 heads. Now, do you see that? Here's heads, head. Here's head, tail, head. Here's tail, head, head. So there's 2 heads there. How many ways can you do that? Well, here's one way, here's another way, here's another way. There's 3 ways of doing that. Over here, to get 3 heads, there's only one way to get 3 heads. Over here, there's only one way to get 0 heads. And the only way you can get 0 heads is by getting all tails. So tail, tail, tail. There's one way of doing it. So that's the number of successes on top, the number of possibilities in the sample space. So it's kind of like I told you before, all of these probability fractions all work out to be basically the same thing. On top, on the numerator, is the number of successes, and the denominator is the number of possibilities in the sample space. Now, do you see why the number of possibilities in the sample space is 8? Well, because you have 1, 2, 3 little slots here that you fill in. There's 2 possibilities for the first toss, 2 possibilities for the second toss, 2 possibilities for the third toss. So you remember our rules of multiplication, or our rules when we learn how to count. This was one of our multiplication rules. If they're independent events, you simply multiply. So it's 2 times 2 times 2 possibilities. 2 times 2 times 2 is 8. So that's how we get the 8 in the bottom there. Okay, so here's the possibilities, here's the probabilities. So we construct this little distribution here. The number of heads can be 0, 1, 2, 3. The corresponding probability is 1/8, 3/8, and so forth. So that's what we got right here. It's the values that the random variable can assume and the corresponding probabilities of the values. So a 1 can only come up, or a 1 is a 3/8 probability of getting 1 head. There's a 3/8 probability of getting 2 heads. There's a 1/8 probability of getting 3 heads. Okay, so that's how you read this little table here. Okay, so here he has the blue box kind of shows you how to work your way through this. Okay, now remember a frequency distribution, we're just writing down what the, how often something can happen. Okay, all right, so let's take an example here. Rolling a die, the sample space is 1, 2, 3, 4, 5, 6. There's only one die. Each outcome has a probability of 1/6. So the chances of rolling a 3 is 1 out of 6. The chances of rolling a 5 is 1 out of 6, and so forth. Okay, so pretty easy, right? I mean, nothing special about that. But now, as human beings, I think we're all a lot better off if we can visualize things. We understand things better if we can visualize. So let's go back to this tossing the coin. The probability distribution for tossing the 3 coins looks like this. This is the table, but then if we're going to represent it graphically, well, here we go. On the x-axis, that's the number of heads. So the x-axis, the horizontal axis, is the values that the random variable can take. So you can get so the random variable is a number of heads. You can the possible values are 0, 1, 2, and 3. So that goes on the x-axis. On the y-axis are the actual probabilities. So the probability of getting 0 is 1/8. Probability of getting 2 is 3/8. So you see how that corresponds? So this is what I think we talked about this before. We call this a histogram. So this histogram represents the probability distribution. Now, just, to make it look nice, you don't have to start with 0 over here. You can put it anywhere you want. It doesn't matter. This is just a cartoon to help us understand things, okay? Okay, so now 5-1 and 5-2, this is rolling the dice and tossing the coins, okay? These are illustrations of theoretical probability distributions. They're theoretical because you don't need to perform any experiments to compute those probabilities. You know that a head comes up half the time and a tail comes up the other half, okay? So, that makes sense. You don't need to do any experiments. However, there are many, many times when we're going to actually perform the experiments to compute the probabilities. Okay, those are empirical. We call those empirical probability distributions. Okay, so now we got this battery packages here. The convenience store sells these things, all these different possibilities. All right, over the weekend, here's what happens. Again, this is the outcome. That is the possible value for the random variable. I may have said that wrong. This is the outcome of what the sales are. Okay, for the 2-pack, you sold 5 of those. The 4-pack, you sold 10 of those, and so forth. Okay, so now you say, well, what's the probability for each of those outcomes? Okay, well, for the 2-pack, how many did you sell? What was the frequency? The frequency was 5. For the 6-pack, you sold 8 of them. Total, what did you sell? 5 plus 10 plus 8 plus 2, that's 25. So there's 25 is in the denominator. 5 for 2, selling 2 of them, the frequency is 5, so 5 out of 25, that's 5 over 25. That's the probability, so to speak, for selling a 2-pack. Let's take 4. There's 10 out of the 25 were sold, were 4-packs, so 10 over 25. Okay, so you're just gathering the data. So this is a theoretical distribution because you can't figure it out ahead of time. You have no way of knowing this. This is all based on what actually happened. All right, so here's a probability. Outcome X and probability of X, P of X. So outcome X is a sale of the 2-pack. This next outcome is a sale of a 4-pack. This outcome is sale of a 6-pack, and so forth. Okay, so each one of those probabilities gets put down here. That's the probability of that happening. Draw the graph using the x-axis for the outcomes and the y-axis. So there it is. Now, what does this really mean? What this really means here, this is an example just to help you understand it. Obviously, the next weekend, things could be different, right? I mean, there's no guarantee that you're going to do the exact same thing the next weekend, okay? But we have to do something. Again, this is a kind of a mundane example, but it illustrates the point. This is gathering data. You gather the data, you come up with the best estimate you can for the probability, and then you use that for whatever purpose that you're trying to use it for. So keep that in mind, that obviously you don't know for sure what's going to happen the next weekend, but this is the best guess that you can come up with. Okay, so here we go. These are that's how to do that problem. This blue table here typically will either be an algorithm or some sort of a important definition for us. Okay, so the requirements for a probability distribution, just like before, all of the probabilities have to add up to 1. And then the probability for each event in that sample space. So up here, the sample space is getting selling a 2-pack, selling a 4-pack, selling a 6-pack. All of those probabilities must be equal to 0. Must be between 0 and 1, inclusive. It's an interval, including 0 and including 1. So the probability has to be somewhere between 0 and 1, including the possibility of 0, including the possibility of 1. So there's an equal sign there. The probability is greater than or equal to 1. It's greater than or equal to 0, and it's less than or equal to 1. Okay, so I'll let you read that. Now you look at these and you say, well, are these probability distributions or are they not? Okay, so take a look at this one. This is, add these up. 0.3 plus 0.4, add them up. It's 7, 8, 10, is 11. So it's 1.1. Well, that's not a probability distribution because, you got to be between, it has to add up to 1. Okay. Here's one that's not, this is not a probability distribution because you allegedly have a probability of a negative number. That's not possible. Okay? All right, so that takes care of 5-1. As always, I know you don't have all the time in the world, but try to read these, speaking of statistics things. They give you a really good background and kind of an interesting application. Okay? All right, and then the applying the concepts is also very, very handy. I urge you to take a look at these. All right, that's the end of this first video, reference 5.1 or 5-1.